Okay, welcome back. So this is the follow-up lesson, the HL extension for the first lesson of topic 4. Topic 9 of the HL syllabus is the first of additional high-level topics, and section 9.1 is simple harmonic motion. So basically an extension of what we learned in lesson 1 of topic 4, which is why we're going to jump into topic 9 while we're talking about simple harmonic motion and cover the mathematical aspects. So this is where we left off. We already saw that these formulas are in the data booklet in topic 9, and we explained that omega 2 pi over t, as we learned in topic 6, obviously still applies. And acceleration is equal to negative omega squared x. This defines simple harmonic motion. It basically says two things. Acceleration is directly proportional to the displacement function, and acceleration is in the negative direction of the displacement function. Now, what I haven't explained is why do we use omega? Why do we use angular velocity in simple harmonic motion? We need a description of the link between circular motion and simple harmonic motion. So I want you to watch this. So what I'd like you to see here is the gray ball is a mass in uniform circular motion around the unit circle. The red ball represents its y component, and the blue ball represents its x component. As you watch this little simulation, you should be able to see that the blue and red balls are the projections of the gray ball along the x and y axis. Let's watch this one more time. And as you watch, you probably realize that both the red and the blue balls are performing simple harmonic motion. So this was to give you an idea of how the circular motion and the simple harmonic motions are linked. Okay, the period and the sinusoidal nature of simple harmonic motion. In the core lesson, we already described that these are trigonometric functions. If you look at the data booklet, you're going to see two functions given for x. It's given both as xo cosine omega t and xo sine omega t. At first, this may look confusing. It's all about how and when you start timing the motion. Basically, let's say you substitute a 0 for t in this formula. What that does is sets that angle to 0. What's cosine of 0? 1. That is the maximum value of this function. So that means when t is 0, the value of x is equal to xo. If you use this function at t equals 0, sine of 0 is 0, which makes the value of this function 0. So when you start observing the mass at t equals 0, when it is at x equals 0, the sine function will give you the relationship between position and the time. If you start observing a mass when it is at its amplitude, which means at t equals 0, x equals xo value, that's when this version trigonometric function will work for that case. Depending on when you start looking at the object, depending on when you start timing one period, you are able to select the sine or the cosine function for the position. Now, whatever you have as a choice for the position function, you will get acceleration as minus omega squared x. I will explain that in a minute, but while I'm here, let me tell you about this one. This is a formula that is given in the data booklet. It's similar to the timeless formula in the equations of motion in topic 2. You see there's no t value in this formula. This relates the angular velocity, the amplitude, and whatever position that you are looking at. So this relates the position along the simple harmonic motion and the corresponding speed, and plus or minus would give you the direction. let's say the position function is x equals xo cosine omega t. That means you start observing when the mass is at equilibrium position. So the way I know that is if you put 0 here, cosine 0 is 1. So at t equals 0, this function will have a value of xo. This is the maximum value of this function. So like any other trigonometric function, whatever is in front of the cosine part is the amplitude of that function. So at t equals 0, the value of x would be amplitude. So this becomes a cosine function, which would look like this for one period. Now, that means corresponding graph of velocity versus time. Let's say we start observing, again at the same point. Obviously, this is coming backward. So at that point, it will start moving backward. But at the amplitude, it has 0 velocity. So initially, at t equals 0, this graph will be starting from 0. At the end of one time period, it will be back where it started. So obviously, it will be same position at tv equals 0. At half the period, it will be at the negative amplitude where it will again have 0 velocity. At quarter period, it will be passing from the equilibrium position, which is where it has maximum velocity, but here it's moving backward. So the velocity graph would have a point there. And at 3/4 of period, the motion is again passing from the equilibrium position, this time going forward, so maximum velocity forward. If you connect those points, this gives you a sine function. So you can write this graph, this is VO and this is negative VO being the maximum value. You can write this as V equals VO negative sine omega t. The VO is the maximum value of this function as the one before, but we know from circular motion that V is equal to R omega, so I can rewrite this as negative, R would be the amplitude, so XO omega sine omega t. Looking at the acceleration function, at t equals 0, the mass is at positive maximum displacement, so its acceleration will be at negative maximum. One full period later, it will be at the same value. In quarter period, half a period during the motion, it will be at negative maximum displacement, which is where its acceleration is a positive maximum. At quarter period, it's at equilibrium position where its acceleration is 0. At 3/4, again, it's at equilibrium position where its acceleration again is 0. When you connect all those points, you get a negative cosine function. So once again, you see, x is equal to xo cosine omega t, a is equal to negative ao cosine omega t. Now, from circular motion, just like we did for v, just like we did for the velocity, I can write a equals r omega squared. This was what we did in circular motion. R is the amplitude, so xo in this context. So I can write that as, I can rewrite this function as a equals, I can rewrite this function as A equals negative. For AO, I will substitute XO omega squared cosine omega t. Please realize that the XO cosine omega t is the position function itself. So this actually also proves that acceleration function is negative omega squared x function, which is where we started discussing the mathematics behind simple harmonic motion. Okay, now I want you to do a small activity. Open this PowerPoint on your own screen and follow the instructions on this slide. Once you do this on your own, you can come back here and continue to my video. Okay, so I have run that simulation for you beforehand, and this is what you were supposed to see. The green line represents the position versus time graph. The red line represents the acceleration versus time graph, and the blue line represents the velocity versus time graph. I have the formulas from the data booklet up here, and the simulation will run. I want you to watch this. So it doesn't matter when you start timing. Let's say you start the timing right here. Because the function starts from 0, that's when the mass is at its equilibrium position and it's moving forward. So you see, this mass is on its way going forward. If I start timing at that instant, that's when the mass is at its positive amplitude and it will have 0 speed and it will be moving back. So the function cosine or sine completely depends on when you start timing the motion. I'll let this run and you can stop and watch again as you wish. Okay, see, this is where I added the acceleration function. I'm going to pause and explain. Please see when the position is 0, acceleration is also 0. Here and again over here. When position is positive maximum, the acceleration is negative maximum, and vice versa. Let's keep it running and add the blue line for velocity. Again, I'm going to pause. So when position and acceleration are 0, which is at the equilibrium position, you see that velocity has a maximum. When position and acceleration have maximum, which is at either amplitude, that's where the velocity is 0, because that's when on a line the motion changes direction. See, this is where velocity is 0, maximum. Let's play again. Velocity 0, maximum 0, maximum 0, maximum 0, and so on. Feel free to repeat this as many times as you like, because seeing this links between the three functions visually really helps understanding the mathematical relationship between them. Okay, now let's talk about the energy in the simple harmonic oscillator. You will remember this from our first lesson, this simulation, but this time I'm going to use this simulation to focus on these energy bar graphs over here, and I want you to watch the kinetic energy graph. So, where is the kinetic energy maximum? See, I have a kinetic energy maximum. Where is the mass? It's at the equilibrium position. Where is the kinetic energy 0? It's reached 0, 0. It's at its amplitude. Now it's on its way back. Maximum, 0 kinetic energy. Maximum, 0 kinetic energy. And you see that when it is at 0 kinetic energy, It's at maximum elastic potential energy. Now these graphs here show obviously including the gravitational potential energy. I want you to ignore that. I want you to look at only the elastic potential energy over here, because we're focusing on the oscillation only. So that was to observe the energy graphs using the simulation. Now let's look at what happens. Remember this formula from the data booklet for velocity. Well, kinetic energy is 1/2 mv squared. We're obviously not changing that. So if you substitute this v into 1/2 mv squared, you're going to have 1/2 m and the square of this function, which is right here, omega squared xo squared minus x squared. Well, good news, this is given in the data booklet as well. Well, where is the kinetic energy maximum? Let's try to find a relationship for the total energy of simple harmonic motion. Take a moment to remember where, at which position is kinetic energy maximum. At x equals 0. Now substitute 0 for the position in this function. What you get is what we have here. So if you put a 0 for the position, which is where the kinetic energy is a maximum, that means total mechanical energy is all kinetic energy. So the value of kinetic energy at the equilibrium position where it's a maximum should be the formula for the total energy that the mass has. Now, likewise, let's try to find an expression for the elastic potential energy in terms of the quantities you're seeing right now. At any position x, the total energy minus the value of the kinetic energy should be the elastic potential energy. So take this function, subtract that function, and you will end up with that function. The total mechanical energy will be conserved as we are assuming the system is frictionless. We call that an undamped system. We are not going to consider damped oscillations in the DP quantitatively. You might only need to consider damping qualitatively in some graphical analysis. That's basically understanding that the amplitude would decrease over time, but mathematically you will not be required to analyze damping. So, summary. Where is the kinetic energy maximum? At the equilibrium position. Where is the elastic potential energy maximum? Where kinetic energy is 0, which is where? At the amplitude, in other words, maximum displacement, which is here or here. So, summary of quantities in simple harmonic motion. So, this line represents one oscillation. This is the equilibrium position and the maximum displacements on the sides. So that would be the position and the amplitudes. At the equilibrium position, acceleration would also be 0, and at the amplitudes, acceleration would be maximum in negative direction of the displacement. At the equilibrium position, velocity is forward or backward maximum value. At maximum displacements, that's where the motion changes direction, and that's obviously why the velocity is 0 at maximum displacements. Well, following from velocity, obviously when velocity is maximum, kinetic energy is maximum, which is at the equilibrium position, and likewise at maximum displacements, kinetic energy is 0. Well, following from that, conservation of energy, where kinetic energy is maximum, elastic potential energy is 0, hence at maximum displacements, potential energy reaches a maximum value. At equilibrium position, restoring force should be 0. This follows from acceleration being 0, or you can also link from elastic potential energy being 0. That means there's no net force towards the equilibrium position because it's obviously at the equilibrium position already. And at the maximum displacements, that's where the force has maximum value, always in the negative direction of displacement vector. To finish up, the simple pendulum formula is given in the data booklet. This is the period formula for the pendulum given by 2 pi L over G. G is the gravitational acceleration and L would be the length of the pendulum for small oscillations only. The mass system, the period of a spring would be given by 2 pi m over k, where m is the mass attached to the spring and k is the spring constant, as we described in lesson 1 from Hooke's law. Okay, to finish up your activity will be sketch graphs of kinetic energy, potential energy, and total mechanical energy in undamped simple harmonic motion on one set of axes. To derive an expression for the angular velocity omega in terms of the spring constant k for a spring oscillation. And to finish up, answer the questions on page 167 and 168 of your workbook. My next video will be explaining the answers to the activities that are listed here. Thank you.